Should I try to connect my presentation?
Maybe, yeah. If you can share your screen, that would be good, so that we are ready to go. So as people are joining, maybe I just want to say something we were telling the speakers. So there are 2-hour slots, which is quite a long slot for a talk. But we were telling the speakers that this is so that they have room to maneuver, and also for people to be encouraged to ask questions. So we're hoping that this is more relaxed and that more interactive, and so that we don't feel bad asking questions, that there will not be enough time, and also that the speakers have enough time to explain things that usually they may not have time for if they wish. But also I told the speakers that if they feel less is more, that's also fine. Basically, this is such a long slot is a buffer. So the talks may be variable in length depending on the speakers. They have full autonomy how to organize, provided that they go easy on us and not go all out for full 2 hours without a break. That's so please do ask questions and ask them early, and so that we can have an engaging time as much as possible in this format. Okay, I think we can slowly start, Slava.
Okay. Yeah, I can start. If you tell me to start, I can start. Yeah.
Yeah, I think we can start.
Okay. Should I just go ahead?
Yes, please.
All right. Well, welcome everyone, and I'm very happy to open this workshop. I'm actually joining you from Russia, where I'm visiting my family for the first time in a couple of years, and so it's going to be, I hope it's going to be a pretty simple-minded talk. I mean, we are all tired of too many online talks, and even though some of us managed to have some vacation, I think we still need more vacation. So I actually told my dad that I'm going to give a talk, this online talk for some people in the UK, and he reminded me of this joke that when they were building a tunnel under the English Channel, then so they invited the applications, and this Russian guy with a shovel shows up. He says that he's going to build a tunnel. So they ask him which company you're working for, and he says, well, I'm working in the company of my brother. He's going to start shoveling from the UK end, and I'm going to start shoveling from the French end. And they ask him, but what's going to happen if you don't meet in the middle? Well, then you will have 2 tunnels for the price of 1. So I hope that this is going to be kind of a simple-minded talk of a Russian guy working with a shovel. So the title of this talk, well, you see it, it's about the RT transformations, how to do RT transformations in a more careful way. And so the ultimate goal of this line of research is basically to develop improved numerical methods for computing critical exponents. So there's a practical side to this which motivates me. And of course, there are already several numerical methods to compute critical exponents. For example, there's a Monte Carlo simulation method, which is a method based on first principles. And then there are various RG techniques. And for the purpose of this talk, I would like to distinguish between perturbative RG and non-perturbative Wilsonian RG, which is going to be the focus of my talk. Then there's also conformal bootstrap, which I'm not going to talk about today. And so basically my goal will be to explain what's the problem with non-perturbative Wilsonian RG and how to do it better. So please interrupt me. So there's a plenty of time, and there's really time for all questions. So what do I mean by non-perturbative Wilsonian RG? I mean the procedure like Wilson taught us. It's a procedure where we take some system which has an energy cutoff lambda, and then we lower this energy cutoff to some lower cutoff lambda prime, for example, lambda over 2. And this change in the energy cutoff induces some change in the action. S goes to S prime. And we are looking for fixed points. So the fixed point equation is S prime equals to S. And if you found such a fixed point, then we can linearize around this fixed point, and the eigenvalues of this linearization are the critical exponents. So this is a well-known procedure. And I think everyone agrees, so most of the people agree that this procedure is correct. There's nothing wrong with this procedure. It works, it should work in principle, but the trouble is that it's not so easy to carry out in practice. And when you try to carry this out in practice, then there are two basic difficulties that you have to deal with. So the first difficulty is that you have to deal with infinitely many couplings, because if you want to do this seriously, your action, it will involve infinitely many couplings if you work with a cutoff. For example, if you have some lattice system, then you have to include the nearest neighbor coupling, next to nearest neighbor coupling, and whatnot, infinitely many. And so if in some sense the fixed point lives in this infinite dimensional Banach space, so some sort of infinite dimensional space, and this is not easy to make precise. So what, of course, you would like to compute, you cannot work directly with an infinite dimensional space. So what you really need is some sort of result where you exhaust. So there is some infinite dimensional Banach space B, and then you find a sequence of growing subspaces B1, B2, and so on, which correspond to some truncations in the space of couplings. And as you increase the number of couplings that you take into account, this this Banach space is being exhausted. And then what you need to do is that you have to show that the renormalization group map, when you truncate it to any given subspace, let's say BI, it has some approximate fixed point PI, and then as the truncation is taken to infinity, then this PI tends to some fixed point in which is the exact fixed point as the truncation is removed. So such results are in fact lacking. So we don't have rigorous results of this kind, and we don't even have practical schemes which I think for which we can clearly be sure that they exhibit this sort of convergence. So yeah, so the picture I'm painting may be a bit more pessimistic, compared to what some practitioners of certain techniques may tell you. So if you're doubting, then if you're doubting, why am I being so pessimistic? If you think that in fact there are some techniques that in fact do perform very well, then you should interrupt me and we can discuss. I will mention some of the techniques and some of their problems along the way. But there is in fact a second difficulty that you also have to live up to, is that
Hey, Slava, can I interrupt a bit? So the usual lore of RG is that not all couplings are important, right? But and that, you know, usually when you're computing something, if you had some reliable scheme, that you can safely truncate part of the couplings. Now that's not always true, of course. There dangerously irrelevant couplings and so on. Is that the underpinning of your concern, or could you elaborate?
Yeah, actually, can you hear me well? Because I keep getting signs that my internet connection is unstable, so I'm a bit worried about how things are going.
There was some jerkiness, but I think I understood every word you said so far. If it gets really bad, I will let you know.
Okay. Yeah. So yeah. So that's what sometimes we say, that not all couplings are important. But in fact, what we mean by that is that when we go to the infrared and we approach the fixed point, there's a certain number of important couplings. These are usually, and then all the other couplings can be parameterized in terms of the values of the important couplings, but they are not zero. So in fact, there are all infinitely many couplings which are non-zero, but the critical surface is finite dimensional, so all couplings can be parameterized in terms of finitely many couplings. But if you do perturbative renormalization group, then you think in terms of this finitely many couplings, and you're fine. But we know that the perturbative renormalization group has some it has some reducible error because it's perturbation theory. So hopefully, it also needs some small parameter and so on. So if you want to really do non-perturbative renormalization group, then you really have to work in this infinite dimensional space of couplings. But then you can say, well, then of course it's infinite dimensional, but it's still in some Banach space, so some norm of these couplings is going to be finite, which means that most of these couplings are going to be small. But there are going to be still many couplings which are going to be significant, and you cannot just truncate to 2, 3, 5 couplings and hope to get accurate results. So typically when people try to do this kind of calculations, I mean, there are some examples when people, even Wilson himself, he tried to perform renormalization group transformation in the Ising model, keeping like 200 couplings, things like that. And he got reasonably good results. But if he just kept 10 couplings, he wouldn't get these results.
Can you also clarify what you mean by results? So I usually have in mind the desire to compute critical exponents. So you're saying that even for critical exponents, you need, I mean, because the common lore is that for critical exponents, at least, you just need eigenvalues, right, of the relevant directions, and that's enough. But do you have in mind all correlation functions?
I mean critical exponents. Perhaps I could put it some other way. So you see, when you found the fixed point, indeed, near the fixed point, there are these relevant directions, irrelevant directions, and we know what happens. Irrelevant directions get suppressed, relevant directions get increased, and so on. But so these relevant and irrelevant directions, they give you some preferred system of coordinates in the space of couplings near the fixed point. But when you are doing the calculation, you are dealing with some microscopic Lagrangian, and you don't know a priori what is the relation between the couplings that you have at your disposal in the microscopic Lagrangian, for example, lattice couplings, and the preferred relevant and irrelevant directions near the fixed points. In fact, determining this map between the microscopic couplings and the relevant directions is a part of the computation that you have to perform. And even though, eventually you could say, well, I'm just interested in finitely many relevant directions, these finitely many relevant directions, they will correspond to some infinite linear combinations of microscopic couplings in, say, your lattice action. And you don't a priori know what those coefficients are. You have to determine them. And the only way to determine them is to include many, many couplings.
Okay, thanks.
Otherwise, the critical exponents don't come out right. Otherwise, it's just to get some qualitative information, but not quantitative, the correct information.
Okay, thanks.
Yeah, so this is indeed important, that you have to keep many couplings. And people who do it seriously, they indeed try to keep many couplings, but even if you keep many couplings, you still don't know if you converge or not. That's the problem.
Sorry, can I also make a comment on? Yeah. So I think so in perturbative approaches, basically, so we can truncate the action only to renormalizable couplings, because basically we can distinguish what are the leading corrections and the subleading corrections, and remove the subleading corrections by hand. And so in this way, when we reduce the cutoff, we don't preserve the physics exactly, but only we only preserve the leading corrections and the subleading corrections. And in this way, we can write a flow that is restricted to a space with very small dimension. But the price to pay is that the RG is not exact, but is exact only as far as the leading corrections are concerned, and we neglect the others. And I don't know, maybe this is related to perturbation theory in the way that we can recognize explicitly from the calculation what are the leading and subleading corrections, but maybe in principle could be done also non-perturbatively. I don't know.
I'm sorry, Achille, but why are you making comments? You're supposed to ask questions. It's my talk. Comments should come later.
Okay, sorry. Yeah. Okay.
Yeah. No, the difference between perturbative and non-perturbative RG is a bit different. The point is that in perturbative RG, you are trying to express infrared physics in terms of UV quantities, and then in the UV, it's your freedom to choose your Lagrangian to contain the minimal number of couplings, just relevant couplings, and then you do perturbation theory in terms of those couplings. So then it's fine. But if you really want to work with explicit, if you want to do Wilsonian RG with explicit UV cutoff, which is lowered, you have to include infinitely many couplings. There's no way to avoid this.
Yeah.
Sure. But let me proceed, unless there are any questions. So the second difficulty is that even the RG map, which maps the action S to the action S prime in general, is not easy to compute if you have many couplings. And so in practice, even if you truncate, then you cannot reliably compute this truncated fixed point PI, for example, numerically. It's a difficult task. And let me give you an example of where this clash between working in practice and working in principle happens. So let me just consider the standard Wilson-Kadanoff RG for the two-dimensional Ising model, where I just consider lattice, you have spins plus or minus 1. And I would like to define block spins as Kadanoff said, which are associated with 4 spins. I define one block spin Ti, Tj. And the formula for which defines this block spin action is given by Kadanoff. I'm supposed to introduce a certain blocking function, B of Ts, which has a property that if you sum over all T's, then for any S configuration, you get 1. So this blocking function basically assigns to various original spin configurations, block spin configurations. And then if I define my new Hamiltonian H prime so that e to the minus H prime of T is equal to sum over S, then, so this is the definition of the Kadanoff, Wilson-Kadanoff transformation of Hamiltonians. But the problem is that even though this formula is simple looking, it's not explicit. So it doesn't define H prime, for example, it doesn't define explicitly the couplings of H prime in terms of couplings of H. So for any given configuration T, perhaps you can compute the value of e to the minus H prime of T by this formula, but yeah, it's not easy to extract the couplings. We would like to parameterize the Hamiltonian in terms of couplings, nearest neighbor, next to nearest neighbor, and so on. But surprising though it may seem, there is no good algorithm to compute the couplings of H prime in terms of a coupling of H. So there was some work, some procedures were proposed by Wilson himself in 1974. There was some recent work by Tom Kennedy, but they're not algorithmic. So they involve some approximations which are not so easy. Yeah. So as far as I'm concerned, there's no good algorithm. So it's not, even if I said, okay, let me just truncate H to 100 couplings and compute the couplings of H prime and see what happens, you can't do it. It's complicated. And so it's hard even to do numerical experimentation.
I'm sorry, I hate to slow you down. I just want to inject quick remark that Peter Hasenfratz and Ferenc Niedermeyer worked on the classical fixed point action in asymptotically free theories. And in that particular case, which you are probably not focusing on, there was an algorithm that worked quite well, but it is not applicable away from the Gaussian fixed point.
Yeah, I think I know what you mean. Indeed, they had a procedure, and I know that paper. But yeah, there was an algorithm and a certain approximation, and but I think it was poorly convergent, and yeah. So no, I don't remember what the full status was.
It was really the classical fixed point action, which is quite useful to have in an asymptotically free theory. And there they had an inverse blocking procedure. It really worked quite well. It was hard to carry out, but I would say it was successful to some extent, at least.
So yeah, maybe you can send me the link just to make sure that it's the same paper that I have in mind.
Okay, sure.
Interesting. Thanks. Yeah. So it's not that like people didn't try, because in the early days of RG, people indeed were interested to carry out this procedure. So they, for example, took each as a sum of various couplings, nearest neighbor, next to nearest neighbor, plaquette, and so on, like I write in this equation. And then you try to compute for just, program a function which computes for given values of k, k1, k2, what are the values of the couplings of k prime. And it's hard to do this. You can try to do this sort of in perturbation theory, and people try to push it, but it has never been pushed like beyond a handful of couplings, maybe 10 couplings. It's really something that people tried for a while and then they basically give up. It's an open problem. So this looks pretty disconcerting, because on the one hand, we all believe that renormalization group is there, it's fundamental and so on, but on the other hand, we cannot compute much just using Wilsonian renormalization group. So people invent perturbative RG, and there you can try to push, but in the non-perturbative context, Wilsonian context, it's hard. So what's going on? And given this disconcerting thing, I would like to give a success story in a related problem, which I find quite inspiring, which is the problem of Feigenbaum universality. So I'm not going to discuss physics. It's a physics is period doubling, some bifurcation, and but the point is that this problem of understanding this universality of period doubling bifurcation, it's been reduced by Feigenbaum, who was inspired, by the way, by Wilson's theory of renormalization group. It was reduced to the following mathematical problem. So the problem is that you are supposed to find a real even function f of x defined on the interval from -1 to 1, which satisfies a certain normalization condition. And you're supposed to find, in addition, a real number, a positive real number a, such that the following functional equation is satisfied. So f of f, so you compose f with itself, you rescale by this number a, and you get back f of x. So f of x is a fixed point of this equation, which is called Feigenbaum-Tsvetanovich fixed point equation. And so this fixed point equation number, positive real number a, such. So this equation is an analog of our G fixed point equation. And the difference, the main difference of this problem from the RG is that it's very easy to do numerical experimentation, because you just, you take this f of x, you expand it in some Taylor series, you plug it into this equation, you truncate, and it's very easy to numerically find solutions, truncated solutions. And for example, you can find very easily numerically that this number a, which solves this equation, is about 0.4, and f of x, has a certain, the first few terms in the power series expansion of f of x, you can also find. But okay, that's approximately numerical solutions. But then it has been proven by Oscar Lanford in 1982. He gave a computer-assisted proof that an exact solution actually exists to this problem. And it's a very interesting proof, because unlike most mathematics proofs, it actually used numerics, but it used numerics in a rigorous way. So the way this proof proceeded is that first he used the computer to find an excellent numerical approximation to f of x. And then he could prove via functional analysis that a certain that there is an exact solution nearby this numerical approximation, which lives in an infinite dimensional Banach space that he defined, and so on.
Sorry, Slava, question.
Yeah.
So this equation is only solved for one value of A? I mean, one may think that for every A, there is a different solution.
No, there is a single A for which there is a solution.
Is there a way to understand why?
There is definitely a way, but I don't want to go into this right now. It's Well, because if you take f of x, you can easily see that because of this normalization that f of 0 equals 1, the shape of this function f gets changed. So you have to perform some rescaling, and there is just one particular rescaling that's going to work. It's not very hard to understand. You just have to draw a few figures.
Okay.
If I can give you an example of why there is a single A. It's related. It's quite similar to the wave function renormalization that you need to perform when you look for fixed points, say for the Ising model. So when you do a Wilsonian RG for the Ising model, say in field theoretic Wilsonian RG, then you know that once you integrate it out, a momentum shell, you have to perform a field rescaling, which corresponds to the eta critical exponent to the wave, and we know that only one field rescaling will work to give you a fixed point. If you pick it wrongly, then it's not going to be there. So it's kind of similar to that. But what I wanted to stress in this computer-assisted proof is that, this fixed point that we are looking for, there's no small parameter. It just sits in the middle of this function space. It's not close to anything. So it's very natural to first find it numerically and then prove that this numerical approximation is actually near the exact solution. And that's what he did. So my dream is that these fixed points for lattice models that we believe since 40, 50 years that they should exist, that they should be in fact found by similar procedures. First, to find an excellent numerical approximation to them. And once you have this excellent numerical approximation, you can, via relatively easy numerical functional analysis, show that in fact there are exact fixed points. But the trouble is that you have to find these numerical approximations, which have to be pretty good, and we don't currently have techniques to do this, as I'm trying to convey. So
can I ask? So, I mean, currently when people do Monte Carlo, they, as far as I understand, they can never distinguish weak first order transitions from second order. So your dream is kind of that we could develop a numerical technique where we can then prove that we are in fact hitting a critical. Is that a fair assessment of?
Yeah. So in these cases where we are there are cases where we're 100% sure that the fixed point should exist. And I think those cases could be settled. So first of all, they will be settled, meaning that they will be proven, and we will also, all these proofs, so how these proofs work, they give for you a procedure, given a good initial approximation, they give you a procedure to iteratively improve it, find better and better approximations which converge. So in fact, these proofs, they also are interesting from a practical point of view, because you will kind of, by turning the crank rather easily, you'll be able to improve your critical exponents further and further.
I mean, I guess from the point of view of lattice, that kind of exists. By going to larger and larger volumes, you can always get better and better, but sometimes it's just impractical to go to such. For example, if you have a marginally relevant coupling directions around your fixed points, then you have to go to exponentially large volumes to actually get anything. So you will have to put corrections. So practically people put by hand corrections and then try to cope with that. But I guess you have in mind an algorithm which is also efficient, right?
Yeah, I have in mind RG. RG works in infinite volume.
Right.
So I do not have in mind something like improve Monte Carlo to make it. I don't have in mind any Monte Carlo magic. I just think how to improve RG. RG is supposed to work, but it doesn't somehow. I wanted to say a few things about field theoretic RG. So this is not really the central to my talk, but I just wanted to say, okay, that there are people who try to do RG in a field theoretic way. There are many people. And the way they do it is that they work with continuum fields and you impose some UV cutoff. The advantage is that you maintain rotational invariance, unlike if you work on the lattice. Then you approximate your action. Well, your action is some infinite sum of various interactions. For example, if you just have a scalar field, then there are various vertices which can have arbitrary dependence on momenta. And then you write an evolution equation for this action. For example, there is the Polchinski equation that I'm sure many people have heard about or are familiar with. Then there is something which is called Wetterich-Morris equation, which is basically a rewrite of Polchinski equation for the one particle irreducible vertices. So it's a bit better behaved, allows for better approximation schemes. But what I want to say is that all of these techniques, they're pretty good. They're pretty good qualitatively, but I think if you think about this, they are. Yeah, I cannot imagine that one of these techniques will one day lead to rigorous control of the using fixed points. It's really, yeah, I don't know. It seems to me that this doesn't look to me as a very promising starting point for what I would like to achieve. So no harm meant to these people who work on these techniques. There's good physics there, but yeah, it looks like the procedure is some irreducible error that's very hard to eliminate. Okay, so, and then I come to the main part of my talk, which is this tensor RG, which is something that I worked on recently. So, but maybe before I go there, so it's maybe a good moment to stop for some questions or discussion, because I've already talked for 40 minutes. So it would be nice to have some. Maybe it's a good moment to stop and talk a little bit.
Maybe I can ask something, Slava. Can you comment on in 2 dimensions, things are easier. And in particular, you have worked, I think, on conformal truncation methods and so on. Are these a good point from where to prove rigorously?
No, not really. So conformal truncation, not conformal truncation, Hamiltonian truncation methods.
Hamiltonian, yes.
Hamiltonian truncation. It's a method which tries to solve a theory in terms of UV data, and it works sometimes pretty well for massive theories, but if the theory in the infrared is conformal, which is the case that I'm discussing here, looking for fixed points, it's tough. So it's not a magic bullet for this kind of problem.
Okay, maybe I can ask a question too. This is probably a bit off topic, but are you making some assumption that the RG transformation is always well defined? I'm thinking about these Griffith-Peirce issues, where in some situations the blocked measure can't be expressed in terms of a Hamiltonian in the same way.
Yeah, no, this is an important point indeed, Patrick, you're right. So In some cases, this transformation that I wrote, this Wilson-Kadanoff transformation, is not even well defined, is known to be not well defined. So, and it's, for example, it's known to be not well defined deep in the broken phase, in the phase of broken symmetry. In near the fixed point, near the non-trivial fixed point describing the critical point of the Ising model, it is believed to be well defined. So in principle, one could. So if we could compute it, perhaps we could do something. But
okay, so this thing might not exist on your whole space.
Yeah.
So maybe I could ask a quasi-philosophical question. You mentioned two ways to organize the space of Hamiltonians, these sort of block spins, and then later the sort of continuum fields of the Polchinski equation. These both seem like they come with some bias, because the first one because we like spins, and the second one because we like free fields. In your opinion, is there an ideal way to organize this? Maybe you'll talk about that in the rest of the talk, or...
No, I don't. I'm not going to give any deep suggestions about what the ideal way is, but indeed, the choice of variables in which you perform your RG is something that you may wish to optimize on. So when you work with spins, you have. So there's no ideal choice. When you work with spins, you break rotation invariance, so you kind of increase the number of couplings because of that. But on the other hand, because of the constraint that s squared equal to 1, you somehow reduce the number of couplings. But also, it's not really clear when you work with spins what are the important couplings. So some people try to do numerical experiments to understand maybe there's some structure, what are the most important couplings. And there is some feeling that at the fixed point, the couplings which have larger and larger range, they will be smaller and smaller. In fact, there is some numerical evidence for that. But we know that at the fixed point, infinitely many couplings will be present of infinitely large range. And when you have, say, a coupling which is a product of 16 spins arranged in a certain way on the lattice, we don't really know what is the shape of this set of 16 spins which will correspond to the most important. It's hard to say. When you work with these fields, people make other assumptions. For example, they say that these vertices, one particular reducible vertices, which they try to parameterize, they make various assumptions that perhaps they can expand them in derivatives. For example, there is this field called function organization group, where they organize, for example, they maybe will try to include all powers of phi, but only up to second derivative or up to the fourth derivative. And then sometimes it gives good results, sometimes it gives not so good results. So yeah, a priori, any space of couplings, as long as you exhaust it completely, should work. But which one is the best? I don't know. Hard to say.
Okay,
so
thank you.
Tensor RG is going to be yet another way to parameterize the coupling space.
So may I ask, if I understand correctly, if there would be some approximation scheme which gets you reasonably close to a fixed point, then your idea would be to design a proof that you are actually close to the real fixed point. It might not tell you the exact form of the fixed point, but then this sort of uncontrolled approximation of truncating would indeed be proven to be good enough. Is that the goal?
It's pretty much guaranteed, yeah. So if you have a method which kind of, you see that it's converging, if there were such a method, I think it would be pretty straightforward for anyone a bit familiar with functional analysis to upgrade it to a proof.
Okay. So then you have that proof, let's say, and that gives you a justification to work with this still not exactly known approximation of the fixed point action.
It gives you justification. It would give you a rigorous estimate of the error that you're making, something that we don't typically have in our possession. So typically our estimate of the error is, increase the number of parameters and see what happens. If it changes a lot, then it's bad. If it changes it, it's good. But the proof would tell you, yeah, the exact fixed point is that much away and the critical exponents are that much away. It would be watertight.
So it would translate to a reliable error of the critical exponent that you derive from the deviation from the fixed point. Okay, yeah, but would be great to have such a thing. So,
but to be very sure, I think the question was already asked. From the numerics, you would need the existence of the fixed point.
You would need existence of truncated fixed points, something that you can compute for increasing truncations, and kind of as a necessary condition for everything to happen, you should see that your numerics are converging with increasing and increasing truncation.
Okay.
So if you see that, then you have to look deeper under the hood, and you have to compute a few other things about these truncated solutions to make sure that this functional analysis machine is operational, but it's basically guaranteed to work because, this functional analysis thing is really, it may look intimidating to someone who hasn't thought about this, but it's really it's a secondary thing. It's the primary thing is to find this procedure, which is the issue of, it's something that physicists should find, this procedure. And then when physicists find it, then mathematicians can prove this theorem. Okay, if there are no further questions, then maybe I can continue with the second part of my talk, which is about tensor RG. Oh, there's something on the chat. Let's see. It's Kostas. Okay, so this tensor RG, we are going to go back to the lattice. It's going to be a lattice technique, and its main advantage is that it's very easily computable. So in case of Wilson-Kadanoff, as I said, it's very hard to compute H prime as a function of H couplings. But for this tensor RG, it's going to be relatively easy to compute. It's just going to be a problem of linear algebra. There are some other little problems that you have to deal with, but hopefully these problems are manageable. So it hasn't been done yet what I want to do, but I feel that this tensor RG is very promising direction to pursue. And I wanted to start with this quote from a review by Leo Kadanoff. So I forgot when Leo Kadanoff passed away. I think it was 2015 or 2016. But before he witnessed this rise of this tensor RG, and he was very curious about it. He wrote a review article, critical review article, let's say. And so he said that that the recent tensor RG workers believe that they can get perfect accuracy when the tensor size chi is infinite. In contrast, the earlier Wilson RG workers felt that arbitrary accuracy would not be available to them. So this really represents, I think he correctly described the spirit of the field, that now somehow the tensor RG people, they think that they can do anything with this new machine. So, and I think they have the right to be hopeful. So the plan of this talk is that, first of all, I will describe to you the main idea of TensorRG. So I'm sure that there are some people who have seen at least some basic things. So I'm sorry if it's going to be very elementary, but probably some people haven't. I will then explain a result that that Tom Kennedy and I got recently. So we got interested in this TensorRG. Actually, we worked for several months on trying to do something about this Wilson-Kadanoff RG, and then everything looked so very complicated. And then we decided to just look at this TensorRG out to get some rest. And I knew that it existed, but I never kind of took it very carefully. But after we suffered so much with the Wilson-Kadanoff RG for a few months, the TensorRG just looked so nice all of a sudden that I got basically converted to this idea. So I explained the proof. It's kind of the simplest result that you can imagine if you want to do something rigorous with an RG technique, is to show that the high temperature fixed point is stable under this RG technique. And okay, surprisingly enough, this was not done before our work, but we have shown this, and this gives some idea about how it works. So I'm sorry, I'm not going to give many references to TensorRG literature, which is quite rich. And in our paper, we give all the references. So if you're a TensorRG person, then please don't be offended. Just I will give some references, but very few. So the first step of this TensorRG idea is to rewrite the partition function of the lattice model. Say you have a certain nearest neighbor action on the lattice, you have to rewrite it as a tensor network. So hopefully everyone is familiar with tensor network. It's just a contraction of some tensors. And usually this step is very easy to do explicitly. You just take your nearest neighbor action, and then what you're supposed to do is that, for example, you have the Ising model, you have possible spin values plus or minus 1. You're supposed to view it as different allowed values for tensor indices. So I hope if you haven't seen it, you will find this understandable. So let me take nearest neighbor Ising two-dimensional model. It's this black lattice, which I put kind of rotated by 45 degrees. So there are these Ising spins S1, S2, S3, S4. And we know that in the lattice Hamiltonian, there is this term e to the minus k S1, S2 plus S2, S3 plus S3, S4 plus S1, S4. So this is the plaquette. And then I'm just declare that this very expression is the value of the tensor component A, S1 with indices S1, S2, S3, S4, which can take two possible values, plus or minus 1. So my tensor A is now defined on, it's a tensor, A is a tensor on the tensor product of V times V times V times V into real numbers. And dimension of V is 2. Because I said there are only two basis elements in V, plus or minus 1, indexed by plus or minus 1. And so I denote this as a tensor by this diagram. And that now the partition function of my lattice model is just a contraction of infinite number of tensors like this. So that's the first step of, before you do the TensorRG, you're supposed to rewrite your lattice model in this form. So if there are no questions about this, you can go.
I have a very brief question. Is it always possible to do, even when you have multiple fields or fermions or something like that? Is it obvious it's always possible to rewrite it, or
I know of no case where it's not possible. Sometimes it requires some ingenuity. For example, if you take, for some reason, if you decide to take the Ising model, which also contains next to nearest couplings, diagonal couplings, then you can also rewrite it, but it's a bit complicated how to write it. So usually by increasing appropriately the size of the Hilbert space V that is basically at your disposal, you can rewrite any model, any local model in this form.
And what about the opposite? Does every tensor network correspond to some Hamiltonian?
Basically, by definition, yes, because you can view. So here on the bonds, you have elements of this Hilbert space V. So let's just introduce some bases in this V.
Right.
And we will introduce on the bonds spin variables corresponding to elements of the bases, and then this gives us
right. Okay, so that direction is easier, right? Because
that direction is easier.
Okay, and I guess when you deal with gauge fields, it's a little bit because they live on links. Then...
So for gauge fields, there is not much literature. In fact, it's an interesting open problem whether this tensor RG could be useful also for gauge fields, whether one can do something useful also for gauge fields.
Okay, thanks.
So then the second part of tensor RG is you have to perform some sort of RG step, which basically amounts to grouping tensors into bigger tensors, which are going to be fewer in number. And just like the usual RG, there are many ways to do the usual RG. For example, you can pick different blocking functions, B of TS, as I said. Also here, there are gazillion ways to perform this tensor RG. So and it's up to you to choose a good way. The choice of a good transformation is a part of the problem. But here, let me just describe the simplest possible transformation, which already illustrates the basic features. So I take 4 tensors, A, I contract them like this. So there are external indices, internal indices that you contract, and I get a bigger tensor, T. Clearly, there are fewer tensors T than tensors A. And since I just contracted partially some tensors, the partition function, which was a contraction of A's, is now a contraction of T's. So the partition function is preserved, which is the property of the RG transformation. It should preserve the partition function. And so you can see immediately what are the main advantages and also what are difficulties of this method. So the main advantage is that this transformation, at least the way I described it, this is the simplest RG transformation you can imagine. It's in principle trivial to perform because you just contract a few tensors. So it's just a problem of algebra. There is no complicated implicit relation to invert like for Wilson-Kadanoff. So the computation of T in terms of A is in principle a trivial problem. So that's good. We solved one difficulty of RG. What's the price that you pay for that? Well, you see that even though this tensor A was defined on the tensor product of V times V times V times V,
Sorry, would it be possible to go a step back?
Yeah.
And ask a more general question? You can leave the slide, that's perfect.
Sure.
I mean, tensor networks are good for, let's say, a quantum ground state where you have an area law. If you go to a critical point, you would have corrections to an area law, typically. isn't it a bad starting point? So the corrections to an area law would mean maybe that the bond dimension has to go very big. So my question is, are these tensor networks not sort of bad starting points for critical points? Do you understand the question?
Yeah, I understand the question. So in fact, these tensor networks, indeed, they have, so here I'm discussing tensor networks applied to classical statistical physics.
Right, but you would like to be more general, I guess, right?
Discuss them for quantum condensed matter physics. The issues are similar. Yeah, for sure. Bond dimension is going to be infinite, as I was about to say in a second. So at the fixed point, we'll have, if you want to describe an exact fixed point, it will be necessarily described by a tensor of an infinite bond dimension. So it's, but also in the case of Wilson-Kadanoff, this Hamiltonians had infinite number of couplings. So it's not clear, infinity there, infinity here. Here we can at least truncate and compute properly. So it's not a priori clear that this infinity is worse in any way than the other infinity. So,
okay.
So when people say that tensor networks are better for gapped states than for critical states, they indeed have in mind is that for gapped states, you can hope to represent them with tensors having, approximate them with tensors having finite Boyd dimensions, while for critical states, you necessarily have to have infinite Boyd dimensions.
So I mean, at least in quantum, where I mean, in solid state quantum, in solid state,
yeah.
The big success stories, I think, of tensor networks were exactly the cases where you had small entanglement, right?
Yeah, but also I can assure you that even for critical states, there are modern tensor network methods, which for the case of 2D Ising model and with the bond dimension of order 100, they can manage to get very good critical exponents and so on. So you can, there is evidence, there is numerical evidence that the tensor networks numerically, they work reasonably well even at the critical point.
I agree. Yeah. Thank you.
So I would like to pursue this idea. So what I was going to say is that we see that this new tensor T is defined on a bigger Hilbert space W, which is the tensor product of V times V. And okay, and so this gives us the first problem is that we can't even compare T with A. So we would like to write down some sort of fixed point equation of the form A prime equals A. But since T and A are defined on different Hilbert spaces, we cannot even compare them yet. And to compare T with A, we have to somehow establish an isometry between V and V times V, which is of course possible only in two cases. Either V has dimension 1 or V has dimension infinity. So we will see that the case of V having dimension 1 corresponds to the high temperature fixed point, and non-trivial fixed point will have a dimension infinity, supposedly. And so if V has dimension infinity, then we choose some isometric isomorphism between V and V times V. Let me call it J. There is no unique choice for this isomorphism. In fact, the choice of the good isomorphism is a part of defining your RG transformation. And then I contract this tensor T with 4 J's on all sides like this. So J is just a choice of basis in V times V. So if I contract T with J, it doesn't change the fact that the partition function is reproduced. So I have now this new tensor A prime, which is again a tensor on V. And so I can now compare A prime with A. So now I have my fixed point equation that A prime is equal to A, or more generally, A prime equals to a constant times A, because a constant just corresponds to an overall factor. It's like a constant term in the partition in the free energy that I can remove without any consequence. So, yeah.
Is there a simple formula you could write as an example for such a J, or is it more symbolic for something very complicated if the dimension of the space is infinite?
I can give you an example. I can give you a very simple example. So V has a certain basis. Let's suppose that V is a span of some basis elements. Let me number them somehow n, where n goes from 0 to infinity. So then V times V is spanned by, of course, tensor products n times m. So it's still a countable set of vectors. So let me just number them in some arbitrary order. And any such numbering will correspond to a particular choice of J.
Okay, I see.
Of course, this is not the most general J. In general, on top of this numbering, you can also apply an arbitrary unitary transformation, and then it's going to give you the most general J.
Yeah, but then if you want to aim at a sufficiently local fixed point action, it's probably very crucial to make a good choice for this J, right?
I think if you don't choose J properly, then the fixed point is not even going to exist. So
I see. Okay.
Yeah.
So can I ask another question? In your Ising starting point, there was a sort of privileged basis given by the action of the global symmetry, right? And can one construct the J so that privilegedness is transmitted through, or is that normal, or?
Yeah, so what you're supposed to do, I think, is you can express your initial tensor. You can split your Hilbert space in Z2 even and Z2 odd states. You can express A in terms of this basis. And then it's natural to require that J maps Z2 even part of the Hilbert space to Z2 even and Z2 to Z2 odd. And then the new tensor A prime will also be manifestly Z2 invariant. Apart from that, there's not much I think you can say in general.
Okay.
About the form of J.
Okay, thanks.
Yeah. So this is what I already said. So the exact solutions of this fixed point equation are possible only if the bond dimension chi.
Slava, I think Adam may have a question. He has his hand up.
Okay. Yeah, please go ahead, Adam. I didn't notice.
Hi. I want to ask, where is the coarse graining here? Because if you had a finite bond dimension, then you would sort of be keeping all of the microscopic information. And so I know if you had a finite bond dimension and you drop some singular values, then you're throwing some information away. But I mean, It seems like you're retaining all the information about short distance correlations at every step of the RG.
Yeah, well, that's definitely something that we should think about. Indeed, what's going on with the coarse graining. And I don't claim that this naive transformation that I'm describing here is going to be adequate. In fact, soon we will see that it's not. But some coarse graining is being definitely performed because we do, since we do perform a trace over here some internal indices of A, then I think it's fair to say that by performing this trace, we do throw out some part of the information about the couplings. In fact, yeah, probably one can show that there are different A's which are not related to the by gauge transformation, which nevertheless, after this step, they give rise to identical T's, which I think is a sign that some information is being removed.
Mm-hmm.
But I haven't thought about this too deeply, so I'm not 100% sure.
But I mean, like the two spins which are on the top right-hand side of the right-hand picture, which are kind of nearest, microscopically nearest neighbors.
Yeah.
Their correlations are still preserved on the left-hand side.
Yeah. I will mention this in a second. So this is just meant to, for experts, this all looks very naive because they already know that this is not going to work, and we have to do something much more sophisticated. And we will see that we will. But I think, at least with this very naive and not quite adequate, as we will see in a second, algorithm, we clearly see advantages, but we don't yet see there are some hidden disadvantages that we don't yet see. We will see them.
Okay, thank you.
So, so in fact, what this allows me to make already some points is that, for example, at this level, one can ask if there are some exact fixed points. I think even this equation, even though it has these disadvantages that Adam knows, but some people who see it for the first time maybe don't see it yet. I think even this equation, it already has some solutions, exact solutions, which I think if we could find, we could claim a fixed point. But in the numerics, of course, people cannot deal with infinite V. So what they do is that you truncate. So what you do is that you find your tensor T is defined on V times V, and then you find some subspace inside of V times V, which is of dimension chi, which is of dimension V, and then you truncate the tensor to the subspace, and then that's your truncation. So that's what people do in numerics. These or similar procedures. And I should say that this is a rather popular research area. And so this was idea in the context of classical statistical physics. It was first proposed by Levin and Nave back in 2007. And just to give you an idea of the size of this research area, this seminal paper has about 500 citations, out of which there are many useful works. And in our paper, we give a sort of review of this literature a little bit. And as I say, the main advantage of this is that the RG transformation are just tensor manipulations. So for example, the bond dimensions of order 100 are completely within reach. And if you take a tensor of a size 100, it's a 4 tensor. So you're basically dealing with, roughly speaking, with chi to the 4th couplings. So it's a huge number of couplings at your disposal, and you should hope that perhaps you can get at least a 2D easing fixed point under your control, and that's what people claim that they can do. But kind of surprisingly for me, this has not been so far done successfully in 3 dimensions. And this is partly related to this problem that I'm going to describe, which is called CDL tensors, as I will mention in a second. Which complicates the algorithms. But I'm optimistic actually that even in 3D, this sooner or later somebody will carry this out and critical exponents will be worked out, even though this hasn't been done yet.
Well, may I ask something? It's probably naive, but I don't know much about these tensor networks. And it seems to me from what you said that, I mean, numerically, it sounds as if you can quickly decide already whether you're flowing into a gapped phase, or maybe you have a potential for it, because the bond dimension is supposed to, if I didn't misinterpret, you have two options. Either bond dimension is 1 or infinite. The ultimate end is that, right, for a fixed point. So if it's 1, that's probably a gapped phase, right? You just have one state you flow to. But numerically, it sounds as if, if you just did a couple of these iterations, that there should be a way to see which way you're moving fairly quickly. Is that correct? Are you moving towards more and more, non-zero terms of the tensor, or meaning bond dimension is going to infinity, or you're moving to just 1?
Well, that's what you would hope for, but as it becomes clear, if you start looking at the examples, sometimes if you don't do anything more sophisticated than what I described, then sometimes it will look like that you are not moving anywhere, because your tensor, because your Hilbert space grows, but most of this growth is kind of polluted by this CDL tensors that I haven't described yet, which confuse you. So you kind of waste, you waste a lot of your Hilbert space on some completely uninteresting things that you would like to filter out. And most of the literature on these tensor networks deals with this problem of how to filter them out.
Right. I mean, that basically, I guess, is the question of this isomorphism. I mean, it's related to that. How do you filter out?
It's even more than that. You will see that we really have to do something more sophisticated to get rid of the tensors. So I think the best way to this high temperature fixed point analysis that I wanted to present, it really puts the finger on this problem very clearly. That you would like to see that if you start near high T temperature fixed point and you flow to it, well, let's try to see how it works out. And we will see that unless you do something more sophisticated, you don't achieve this convergence.
Okay, thanks.
So this is what we would like to see, that if we start near the high temperature fixed point in some small neighborhood, then we would like to see that this tensor Rg converges to this. Some form of tensor Rg converges to this fixed point. But what is this high temperature fixed point? Well, it's very simple. It's a tensor which contains only one non-zero component. So let's call this, it's a tensor on the Hilbert space of size 1. So let's call it the only basis element 0. And the only component is 0, 0, 0, 0 is exactly 1. So I will denote this tensor by this blue dot. And clearly this is a fixed point, because if you contract this tensor with itself 4 times, then you get again 1. And so what you're supposed to do is that you're supposed to identify this vector 0 tensor 0 with 0. This is the choice of this isomorphism J, which is unique. And well, and then A prime is equal to A. So it's a fixed point, very easy. And what we now would like to do is that we would like to take this tensor and we would like to perturb. So we now consider a different tensor A, which is going to be denoted by this empty circle, which is a perturbation of this tensor fixed point, high temperature fixed point tensor, blue tensor. There is a certain perturbation delta A, which by itself can live in a Hilbert space of arbitrary dimensions. So let's consider infinite dimensional Hilbert space. It can have an arbitrary number of couplings. And the thing that I assume about it is that it's small. So it has a norm of order epsilon, where epsilon is a small number. And now, okay, so here comes, since we are dealing with infinite dimensional objects, we have to discuss what is the appropriate norm. But it's not very hard to guess what the good norm is. So in fact, the appropriate norm is the so-called Hilbert-Schmidt norm, is just, you know, what anyone would guess is just the sum of all elements of the tensor squared, square root. So this is the Hilbert-Schmidt norm that we are going to use to measure the size of tensors. Very natural. And this norm is good because it's invariant under change of basis in the Hilbert space, and especially it's good because it's well behaved under contractions of tensors. So, for example, if you take two tensors A and B, you contract them using one index, you get a new tensor C. Well, it's very easy to see by Cauchy-Schwarz inequality that the Hilbert-Schmidt norm of C is smaller than the product of norms of A and B. I spare you the check, but it's a very natural choice of norm. Okay, so this is the perturbation delta A, and we would like to see that after the RG step, this perturbation gets reduced in the norm. This is the goal. Well, before we start doing that, I would like to state some other obvious, relatively obvious assumptions that we are free to make on this perturbation. For example, I'm going to assume that this perturbation is invariant under lattice symmetries, horizontal and vertical flips of my lattice. That's not essential, and in fact, in our paper, we treat the general case of perturbations which are not invariant under lattice symmetries. Another thing that I'm going to assume without loss of generality is that the 0, 0, 0, 0 component of this perturbation, which is vanishes. Because I already had the leading term for which this component was 1. So if my perturbation has this component non-vanishing, then I'll just add it to the leading term and then rescale my tensor. It's no problem. And finally, a more subtle point is that I can assume that this sort of components of my perturbation, where 3 indices are equal to 0, and any fourth index, one of the fourth indices is not equal to 0, is going to be denoted by x. X means not equal to 0. So even though the whole tensor is order epsilon, I can actually assume that these particular components are of higher order, of order epsilon squared. So why is this the case? Well, because we should remember that our tensors are defined up to a gauge transformation. So I can do a change of coordinates, a rotation in my Hilbert space, which preserve, of course, if I do this rotation or a change of basis, then it's still the case that the partition function is reproduced, but the tensor changes. And so the claim is that by doing this rotation, I can set these components 0, 0, 0, x to be higher order than everything else. Someone has a question? So that's just an easy computation, but I would like to go through it from some detail because it illustrates a certain point that is going to be useful later in a slightly more complicated context. So a gauge transformation, as I said, it's a rotation in the Hilbert space. Rotation is a unitary matrix. Well, here I'm dealing with real tensors, so it's an orthogonal matrix G, well, infinite dimensional matrix G. And so what I'm doing is that I'm inserting on every horizontal but also vertical bond of my tensor network, I'm inserting G transpose. So GG transpose is equal to identity. So my tensor network is unchanged. And I call this this part, well, here I'm only transforming the horizontal bonds for the moment. So I'm calling G transpose AG, I'm calling it A tilde. And then the claim is that by choosing this G appropriately, I can rotate this matrix elements to order epsilon squared. Well, it's kind of easy to understand what's this appropriate rotation. You have to define a certain vector Vi, which is made out of these components that you would like to eliminate. And then, this vector Vi, it kind of points in this direction, where the what's happening here? It's not writing. Where this component is order epsilon and this component is 1. And what you need to do is that you have to rotate this vector to the vertical direction. So this is the rotation matrix G that you have to apply. So this cannot always be done, and it's easy to see that it modifies because you have to apply it on. If you just have to apply it to on one side, then you could set that what you can achieve is that these components are order epsilon squared. So this is sort of an easy technical point. So, okay, now let's proceed to our RG transformation. So I take my tensor A and I form this tensor T, which is just a contraction of 4 tensors. And I start looking at what is the structure of this tensor T. So I expanded the perturbation. So the 0th order term gives me just a fixed point. Then I look at the leading correction, which corresponds to inserting just one perturbation somewhere, for example, here on the upper right corner. And here I see a problem, because I see that since all these blue tensors are 1, this particular contraction, where I just inserted one perturbation, is exactly equal to the component of the perturbation where the 2 indices are 0, 0, and the 2 other indices are x and y. So there are these corner components. And what we are finding here is that the corner components, they are left invariant under this transformation. So that's what related to what Adam was saying before, that the correlations between vectors x and y are not reduced in size. They are exactly passed on to the next RG step, and they have exactly the same norm as before. They're not reduced. And well, this may seem puzzling because we expect a renormalization group to converge at least exponentially and perhaps super exponentially to the high temperature fixed point. So before I start discussing further this problem, I don't know, maybe there are some questions, because it's starting to get a bit technical. I'm afraid that people are going to get lost. Okay, if there are no questions, I wanted to say that what is the relation of this problem to the so-called corner double line tensors, which are called CDL tensors. So the CDL tensors have this structure. This is this diagram over here. So let us suppose that our Hilbert space actually is a tensor product of 2 smaller Hilbert spaces. And my tensor, even though it looks like, okay, it introduces some correlation between the 4 indices on 4 sides of the tensor, in fact, all correlations, they have this pairwise structure where, so this index is only correlated to this index, this to this, this to this, this to this. So if I have such a tensor, and if I form a partition function out of this tensor, then the partition function is trivial because I can, if I contract all the indices, I just get a bunch of closed loops that I can immediately evaluate. So here was one CDL tensor, here was another CDL tensor. So there are infinitely many tensors, but in fact, this partition function is immediately evaluated, and it's clear that it does not contain any long-range correlations. So all the correlations are ultra short range in this latest model. So it's clear that these CDL tensors are totally trivial and totally uninteresting. But what happens is that if you don't do anything about them, if you apply your tensor RG transformation, your tensor is polluted by the CDL tensors. It's polluted by, and so especially if you do numerics, it's very annoying because it's hard. You would like to push the dimension of the space V, of the bond space V, as high as possible, and it's very wasteful to if some part of this dimension is being occupied by these useless CDL tensors which do not correspond to any interesting physics. So much of this tensor RG literature is devoted to devising various techniques to filter away these CDL tensors. And it's more complicated than it might seem because, okay, if it's an exact CDL tensor, then it's very easy to filter it away. You just see it and filter it away. But you may also have some perturbation which is not exactly CDL, so it's kind of almost CDL, but it does couple a little bit to other degrees of freedom. So it's not obvious how to filter it out efficiently. And so people spend a lot of effort thinking how to do it. And there are various proposals in the literature, in the numerical literature out there. And, being numerical, they have a slightly different motivation from us. So they are all necessarily involve some truncation and so on, but we were inspired nevertheless by one of these proposals by Evenbley and Vidal back from 2014. And so in our tensor RG algorithm that I'm going to describe, it's kind of people who know Evenbley Vidal proposal, maybe they will see some echo of it in our algorithm. So unless there are any questions about CDL tensors, I'm going to describe our modified tensor RG transformation. So as I said, the naive RG transformation, tensor RG transformation, it doesn't have the property that if the perturbation is order epsilon, then after the tensor RG, it gets reduced in size. So we would like to devise a tensor transformation which reduces these corner components, removes them. So this is going to work as follows. The first step of the RG transformation is going to be the same as before. Again, I'm going to form this tensor T as a contraction of 4 tensors. But then I'm going to do something different. So I'm going to work with this tensor T. I'm going to perform several steps on it. The first step I'm going to do is to act with the so-called disentanglers. The point of this disentanglers is that it's like a gauge transformation, but it's going to act on 2 indices. So this tensor T has 2 indices coming out left and right. And so I'm going to act with an orthogonal matrix R. in this 2-index space, and with the transpose of this orthogonal matrix R on the left. So we will see in a second why they're called disentanglers. So once I acted with disentanglers, I defined a new tensor S. And in the third step, I'm going to represent this tensor S as a contraction of two tensors, which I call S up and S down. So you see, the tensor S has 8 lines coming out of it. I'm going to group them into 2 groups, 4 and 4, and there is this 5th index along which these 2 tensors S up and S down are contracted. So in the numerical TensorRG literature, it's full of this sort of decompositions of tensors, and usually it is performed as a singular value decomposition. So in our work, this decomposition is not going to be a single value decomposition, but it's going to be closely related. So after I define these tensors as up and as down, I'm going to reconnect them. So I'm going to, you see, the tensor as up has 2 indices coming up and 1 index coming down. So I'm going to now contract them in the opposite order. So I'm going to contract, I'm going to put the S down tensor on top, S up below, and I'm going to contract these 2 indices, which were these indices here. And so this is going to define a new tensor U. Of course, since I'm just changed the order of these tensors S up and S down, my tensor network, which was a contraction of tensors S, it's equally can be reproduced as a contraction of tensors U. And finally, my tensor A prime is built out of this tensor U by just contracting it with a couple of isometries on 2 sides, because I have 2 indices coming up on the left, on the right, so I have to apply some isometry here. Okay, so that's...
It seems you're treating the 2 different directions differently. So you might be losing manifest rotational invariance. Is that does that happen, or?
Yeah, that happens. So this transformation, it preserves flips, but it doesn't preserve rotation by 90 degrees.
And couldn't you treat them somehow? Is there no way to treat them usefully in the same manner?
I'm not sure.
I guess, yeah, I guess I knew the answer to that. Otherwise, you would discuss that.
Yeah, it's probably yes, but it would require probably even further complications. But so we settled for this.
But in the paper, you don't even assume rotational invariance, so you don't care, I guess.
Yeah, in the paper we don't assume, because we know that in principle any perturbation of the high temperature fixed point has to flow to 0, including those which don't preserve lattice symmetries, and that's what we show.
Right, but presumably for actual critical points, one may have to worry about preserving this.
Well, it's yeah, perhaps, but the people who do numerics, they don't. So this algorithm, as I said, it's modeled after this algorithm of Evenbley and Vidal, and the algorithm doesn't preserve the rotation invariance either. So, and somehow they do get good results for the 2D easing. So I would imagine that this just means that their fixed point tensor, it's not manifestly rotationally invariant, but nevertheless the physics in the horizontal and vertical direction is just related by some rescaling. So it's kind of yeah, it's kind of sad that we have to sacrifice this rotational variance, but what can we do? We sacrifice it to computational power. Any other questions?
Is it obvious what J is, and moreover, what is the decomposition, the initial decomposition that you turned this single line? Presumably, it's not unique. You said something about singular value decomposition, but
So
more than one choice.
Yeah, no, it's crucial. So this decomposition S and S up, S down, it's a part, you have to do it in a smart way. Unless you do it in a smart way, it's not going to work. I'm going to say a few words about what's the point of this whole. I mean, this probably looks very weird for people who see it for the first time. It looks very ad hoc. I'm going to motivate it a little bit. Why is this a good idea, this sequence of transformations? J, on the other hand, for the high temperature fixed point, it's not really, there's very little to worry about, because you just you always map 0, 0 to 0 or 0 to 0, 0, so that the leading part of the tensor is a fixed point, and everything else, since everything else gets reduced, for the high temperature fixed point, you don't need to worry about. You can basically assign it arbitrarily, the rest of J. Because you only worry about the norm of the rest, and you want to show that it gets reduced. But for the non-trivial fixed point, it's going to become, it's going to become an issue. So why are we doing this? The point is this. So why do we have to apply these disentanglers? The point is that if you look at the second order term, let me say first the following thing. So there are two steps here. There are two ideas here. First, there is this idea about disentanglers. And then there's this idea about reconnection. So let me first explain why this reconnection is a good idea, why it's going to achieve what we want to achieve. And then I'm going to explain that even though reconnection is a good idea, it would not work without disentanglers, because there is some there's some problem out there. So let's suppose first that we don't apply any disentanglers. So S is equal to T, so disentanglers are identity, and see why this reconnection is a good thing to do. Well, because recall that the problem that we were having with trivial RG transformation is that there was some correlation between this angular indices of the S tensor or of the T tensor, which were large, because they were passed away from the previous step of RG transformation to the next step of RG transformation, basically unchanged, and we want to eliminate them. So let's see what happens. So these correlations are large. So when we represent S as a product of two tensors, S up and S down, of course, these correlations, they are not going to go anywhere. So they're just, given that S has large correlations, it means that in the S up tensor, there's also a component, a significant component, which correlates these two indices, which I drew here a red line. And similarly, in S down, there's also this angular correlation that exists also on the other side. But now, when we reconnect the tensors, so there were these two correlations, which were order epsilon, recall. They get contracted to each other and they become something which is order epsilon squared. So after I reconnected, this problematic correlation, it goes away. You know, I'm no longer left, or at least this particular correlation, it went away, and it, you know, it got contracted away, and I got rid of it. So that's why reconnection is a good idea. It eliminates certain components of order epsilon and makes them order epsilon squared. Okay, that's good.
Sorry, Slava, can I ask something? Ciao, by the way. Is there any physical intuition on this reconnection? Or apart from the fact that the correlations are going from order epsilon to order epsilon squares? I have no intuition on this tensor network. So it seems to me something, as you were saying before, ad hoc, just to make them jump from order epsilon to order epsilon square.
Well, the physical intuition, one can give a certain physical intuition. I can try to give you some physical intuition why what we are doing here has some sense. Imagine working in the continuum limit somehow. Okay, so we take our plane, we divide it into some squares, and then we kind of, so a certain tensor, you can think of this certain Hilbert space which lives on this side of the square, here, here, and here. And then when we perform this naive RG transformation, we just glue 4 squares and we get a bigger square, something like that. And when we do this, there are some degrees of freedom which live near the corners of the square, which somehow, the fact that you glue the squares, since they always live on the boundary of the space that you're gluing, they somehow don't feel that you glued anything, and it's these degrees of freedom which are problematic, that they remain correlated. And so this reconnection thing, it kind of gives the transformation that you're performing a spirit of something which takes place not only on this square, but also on a shifted square. Because this reconnection, it shifts the things by one lattice spacing. And so because of this shift, the degrees of freedom that were on the boundary in the corner of the naive transformation, they are no longer in the corner, they're kind of in the middle of the shifted thing. And so you can hope that by putting them in the middle, you can more efficiently coarse grain away these correlations. So you should do something, you should do some sort of transformation which doesn't allow things to be always in the corner. And the way to do this is to shift things around by this reconnection idea.
Good. Thank you.
That's how I think about it. For what it's worth.
I mean, it sounds to me like the reconnection is kind of devised to, quote unquote, integrate out these short loops which are polluting everything, right?
Yeah.
In some sense, yeah. This is the idea. You have them still in the tensor, and if you could only just contract a little bit with the neighboring things, they would just go away.
Yeah. So that's why you should. But now I wanted to explain why this reconnection wouldn't work without disentanglers. Well, because what you should be worried about is that what happens if somehow here, if there is a certain correlation between these degrees, these two indices which point to the left, to the right, sorry, which are now denoted by the blue line. So if there is some correlation out there, then this correlation is going to be passed to this S up and S down tensors, because the S up and S down tensors, they're supposed to reproduce this correlation. And then we reconnect. When we reconnect, this correlation will appear here. So by reconnecting, you will eliminate some correlations that you wanted to eliminate, but you will create some other correlations that were actually unwanted. And you might very well, you don't want here any correlations which are over the epsilon, which means that here you should not have any correlations over the epsilon squared. And how to eliminate correlations? Well, we have seen this already in at the beginning of my presentation of the tensor RG, that you can apply by applying a gauge transformation. We were able to set certain components of this tensor, which were the components 0, 0, x. From order epsilon, we were able to reduce them to order epsilon squared, just by applying gauge transformation. So similarly, now what we are going to do is that by applying a disentangler, which is a gauge transformation on 2 lines, we will remove, so as I will show now, these blue dangerous correlations actually do exist. They do exist. And by applying disentanglers, we will remove them. And only after removing them, we will perform this decomposition and reconnection, and then everything will go smoothly. So that's the idea. So in fact, in fact, okay, you now understand. I think I explained the basic idea. So the dangerous diagram is this one, is when these indices are x and x double prime, so these are some non-zero indices, and when the exchange index here is also non-zero, x prime, so this corner component of the perturbation tensor is order epsilon, so this diagram is order epsilon squared. And that's precisely the diagram that we don't want to have in the game. So we need to kill this diagram, and we kill this diagram by applying disentangler. So that works exactly like with the gauge transformation. And once we kill this diagram, then, as I explained, after the reconnection, we are not going to have any corner correlations of order epsilon. So okay, there are some technical details which I think I'm going to skip, but so these are disentanglers, as I said. And then basically you have to think a little bit, yeah, so you kill these things over the epsilon, but what do you, what are you left with? And it turns out that you're left with something which is order epsilon to the power 3/2. So perhaps you would have expected naively that it's going to be epsilon squared, but for some reason there are some terms of order epsilon cube floating around, and when you take a square root, it becomes order epsilon 3/2. But nevertheless, when this settles, you get the following theorem that we proved, that if your initial tensor is a perturbation of high temperature fixed point by something of order epsilon, and you perform this more sophisticated RG transformation that involves disentanglers and reconnection, as I described, you get a tensor which is high temperature plus something which is orders epsilon to the 3/2. And so this implies that the tensor RG converges super exponentially fast to the high temperature fixed point. So that's basically the end of my talk. And I would like to be optimistic. So I think tensor RG has great potential, and we felt when we worked on this with Tom, we felt that it was various things which usually are quite technical in rigorous RG studies. For tensor RG, they just go through very easily. So we felt really that it was a nice machine to work with. And so even though more work is needed to fully realize the potential of this method, I think it's worth an investment. And so I actually believe that currently this method is probably the leading candidate, my leading candidate for solving the dream problem of constructing a fixed point for the three-dimensional easing model at the critical temperature. So I hope that there's going to be rapid progress on this in the next few years. Thank you.
Thank you, Slava, for a wonderful talk. And people clapping, maybe you want to unmute so that this doesn't sound like a... That's much better. Always one person clapping is like a sarcastic clap. Any questions? There were a lot during the talk, but any questions at this point? So I actually have something. Could you go back to this decomposition of up and down?
This one?
Yes, yes, exactly. So I would naively think that what would be an easier thing, well, what would be a cleaner thing, let me say, not easier, is to decompose into 3 corners connected by single lines and then reconnect. And then you would just get rid of all these corner correlations. But that might be technically difficult. So instead of...
So what do you mean? Something like that? Yeah, I'm not sure what you mean.
So instead of S up and F's down, let's say you put these green blobs into 4 of them connected by single lines, and each of them have 2 lines out.
But you mean, but then we will go. I think you want to connect. You want to represent S again as this.
Yeah, but that's just going back, right? It's not getting you anything.
No, it's not quite going back because we performed the disentangle transformation.
Well, the idea was not to use the disentangler. I think the reason why I'm asking this is if you go to 3 dimensions, then this S up and S down, would it require then 2 kind of disentanglers in the orthogonal directions? I mean, would it work in a higher dimension? Let me put it that way.
I'm sure it will work. I'm sure it will work because there's going to be this. Yeah, I'm sure it will work, but we haven't worked out the topology. It's one of the open problems that we list in our paper, but we haven't done the 3D case. It would be interesting to do it. This transformation, in fact, we write this S up and S down abstractly, but in our work, all the tensors, they come in these contractions of. So our initial tensor is a sum of 2 tensors, high temperature fixed point plus perturbation. So all of our tensors that we are operating, they're contractions of these basic components. So in fact, S up and S down, even though I kind of write it abstractly as a semicircle, we have an explicit expression for it in our paper, which is not surprisingly given as a contraction of a certain, S up in our paper is given as a contraction of 2 tensors like this, of some tensors like this. So in fact, we do have a representation of S in this form, as you're suggesting.
Mm-hmm.
So
I guess what I was suggesting is the way you wrote it. Of course, it looks kind of going back, but somehow that you don't have corner correlation in the internal indices, that you got rid of those by summing, just partially summing in the Hilbert spaces there. Because at the end of the day, that's what you do, is just you do it in one direction, and the rest you get rid of by this gauge transformation. And it sounds like it would be have to tune to a particular problem, but maybe I'm wrong. Maybe it can be made very general.
No, but if you look at the literature, in fact, that's part of the reason why they haven't generalized it yet to 3D, is that they this Even-Blevidal algorithm, it has never been realized in 3D. There is some other algorithm that people hopefully hope that they will realize in 3D, which is called GILT. But that algorithm, that GILT algorithm, somehow, the nice thing about Even-Blevidal is that even though in the original paper it's formulated in the language involving truncations, you can kind of clean it up in a way which avoids all truncations, and you still get something non-trivial. And that's what we basically did. But in this GILT algorithm, which is something that people hope to apply in 3D, I tried to think about this, but it seems to me that if you clean it up from truncation, you're left with nothing. So it's kind of, truncation is a very essential step of the algorithm, which, so I'm kind of a bit puzzled about whether it can be formulated in a setting without truncation, which is what we need to do. Okay, so people are still thinking about this.
Okay. Are there any more questions, final questions? We went, believe it or not, a little bit over time. I did not expect that. But
yeah, I would have one more question, if I may. So as you explained, these CDL tensors prevent you from converging to the fixed point. And I mean, in the Wilson RG, there are, for example, sharp momentum cutoffs, which would make the fixed point action non-local. But are there any similar effects? Is there an analog of the CDL tensors in the Wilson RG? So just to get a better understanding of what these things are?
Yes and no. So I think very, very roughly, you could make a very, very rough analogy between the CDL tensors and how should I put it? So when you write down the Wilsonian action, usually there is a little bit of freedom how to shuffle interactions between different terms. So sometimes we call it field redefinition freedom. So sometimes you can write an equivalent action which has slightly different couplings, but in fact it's related to the old action because you just redefined fields.
Mm-hmm.
And when we write down a Wilsonian RG, we usually commit to a certain particular way to fix this field redefinition freedom.
Mm-hmm.
And if you make a very unfortunate choice to fix this field redefinition freedom, it may somehow destroy your fixed point.
Okay.
But in practice, this does not happen. So this field definition freedom is usually not a big deal. You fix it in some way, and even though it's arbitrary, it still does not prevent you from finding a fixed point. So similarly, these CDL tensors, they're also kind of a redundancy. It's a pollution, it's a redundancy. which is related in a sense to the field of definition redundancy, but it's much more dramatic because it accumulates much faster, it's much bigger, and indeed it prevents people from finding a fixed point.
Okay, so this is a kind of potential disadvantage of this tensor RG, which the Wilson RG doesn't suffer from. But then if you are clever enough to get that problem under control, you seem to think that tensor RG is ultimately more successful.
I think you summarized it very well.
Okay. All right, thank you very much. This was very interesting.
Okay, Slava, there's a session for questions for people who would watch the recording in the afternoon, 15 minutes. I don't know whether there will be anybody who wants to ask questions, but if you can make it, it would be very helpful.
I hope to be there.
Yeah. So, and of course, also the audience now who listen to the talk will have a chance maybe after everything settling down. If you have more questions, you will have a chance to ask Slava. In fact, in any of these discussion sessions, I mean, they're primarily based, aimed at talks which were given recently, but if the person is there, you should feel free to ask a question. Okay, so let's adjourn, and thank you again, Slava, for a wonderful talk, and we will see some of you in the afternoon, others may be sleeping by then, but thanks again, and have a good day. Bye.
Bye.